are literally thousands of miles of pipes and tubing in industries such as those that process steam or chemicals, refine oil, or produce electrical power. In fact, if you took all the piping in your plant and lined it up in a straight line, it would probably stretch all the way from Maine to California. In every plant, these numerous pipe and tube systems carry liquids and gases from one point to another. They keep everything connected. And without this intricate network of metal and plastic vessels, the plant couldn't operate. Even a small leak in just one pipe or tube can affect the operation of an entire system, which means that maintaining this network is a big job and an important one. Inspection and repair of pipes and tubing is an everyday, ongoing part of your job on the maintenance crew. So you should take the same kind of care working on them as you do when working on other plant systems and components. Let's have a look at some of the things you should watch for when inspecting pipes and pipe systems. Take, for example, a piece of pipe that is badly dented. Such dents can affect the strength of the pipe. If you see any badly dented pipe as you inspect pipe systems, it should be replaced. Always check for rust or corrosion, too. You may find that a fluid, caustic or acid, from another part of the system is dripping on the pipe, causing it to corrode. Be sure to find the source if you see that rust or corrosion is developing on a pipe or around a fitting. If you see any shiny spots on a pipe, it usually means that something has been rubbing against it. If this continues, it'll cause the pipe to wear thin in that place. This situation often indicates that additional supports or protection for the pipe is needed. Another part of pipe system inspection is to check the thermal insulation. If you find soft spots on the insulation, it means that something has been hitting against it, or that the insulation has gotten wet. This type of damage should be clearly visible. If you see that the insulation has been or is wet, find out what is causing it. It could be that something wet was sprayed on the insulation, or that there is a leak in the pipe. If you suspect that the pipe is leaking, you'll have to remove the insulation. If you aren't sure what kind of insulation it is, assume that it's asbestos and wear an approved face mask, goggles, and gloves. And take any other safety precautions your plant may require for personnel working with asbestos insulation. Once you've found the cause of the wet insulation and repaired any leaks or other damage, the insulation should be dried quickly using system heat to reduce the possibility of corrosion. If the insulation can't be dried, it should be removed and replaced with new insulation. Inspect all mechanical connections, such as flanges and unions, for any sign of leakage. Tightening the connections may be all you have to do to stop a leak. If the leak doesn't stop, make a note. Give it to your supervisor so that it can be repaired at the earliest opportunity. On systems that are alternately heated and cooled, inspection of the mechanical connections is absolutely essential. Constant heating and cooling may loosen the studs and bolts of the connections. Once you've inspected the piping systems and checked for dents, shiny spots, and leaks, you're ready to make any necessary repairs or replacements. But before we see how pipe is sized, measured, and fitted to make repairs or replacements, take time to look over Chapter 1 of your text and clear up any questions you might have about inspection procedures with your instructor. Now we're going to talk about how pipes are measured and listed according to their size and schedule. We'll also see how a line of pipe is fitted into a system as a replacement. We'll start with how pipe is measured. The first measurement taken is the outside diameter of the pipe. This is the distance from the outside edge on one side across the inside opening to the outside edge of the other side. This measurement is called the OD, outside diameter. The inside diameter is measured next. It's taken from one inside edge of the pipe across the opening to the other inside edge. This measurement is called the ID, inside diameter. The difference between the outside diameter and the inside diameter is called the wall thickness. Now, the wall thickness varies according to the pipe schedule. The schedule can be compared to pressure ratings. As you increase the pressure rating of 4-inch pipe, the schedule goes up 40, 80, 120, and so on. When there is an increase in pressure, the pipe must be increased in strength. The pipe is listed by size and schedule. However, pipe size is identified in a somewhat unusual manner. The listings give a normal size, that is, a size that varies from the actual size of the pipe. The nominal size listing is always smaller than the actual size of the pipe. So, if you ask for 4-inch pipe, you won't get a pipe that is 4 inches. You'll get one that is larger than 4 inches. Moreover, you'll see that some measurements remain constant and others vary. The outside diameter of a pipe is always constant, but the inside diameter varies with the schedule of the pipe wall. Now, let's talk about how a piping system is built. If you look closely at a piping system, you'll see that components and pipes are fitted together with a variety of connecting devices. In building a system, there are different ways to connect pipes to other pipes or to components. The connectors can be flanged, usually by threading or welding, or they can be welded. Flanges are connected to pipes or components in several ways, and flange faces come in different styles. We'll talk about the flange connection first. This flange is threaded to the pipe. It's done by threading the flange onto the pipe until the pipe end is approximately 1 thread from the face of the flange. This will prevent the pipe from interfering with the flange faces when the joint is made. If the pipe were threaded through the flange, it would prevent the 2 flange faces from meeting and forming a seal. A threaded flange has some disadvantages. Threaded connections have a greater tendency to leak than do certain other types of connections, and the pipe at the threaded point is weaker than at other places on the pipe. To provide a stronger flange connection, a lapped or Van Stone flange can be used. The flange is slipped on the pipe, and then the pipe end is lapped or faced off, as you see here. This type of flange can be rotated to line up with a connecting pipe. A gasket is used between the faces of the flange to provide a seal. The strongest flange connection is the welded flange. It has a welding neck, which is welded to the pipe. Again, a gasket is put between the flanges to seal the connection. Whenever you're replacing flange connections or components, remember that the new flange face must be exactly like the one you're replacing. If it's not, there will be leakage when the system is pressurized. So let's take a look at the types of flange faces you will find. There are 3 common faces: raised, male and female, and tongue and groove. Now, this is a raised face. The raised portion, often called the boss, can be raised anywhere from 1/16 to 1/4 of an inch. The second type of flange face is the male-female. The male face has a raised portion which fits into the female face when the flanges are connected. A modification of the male-female flange connection is the 3rd common type of face you'll find, the tongue and groove. One flange has a raised portion that fits into a groove on the other flange. This type of connection provides a very effective seal against leakage. Usually an O-ring is put into the groove to act as the gasket seal. In addition to the flange, some pipes are just threaded together with a union, nipple, or coupling. These types of simple connections are found mainly on low-pressure systems or on very small piping, 2 inches or less in diameter. On large pipes and in high-pressure systems, pipe connections are usually welded or bolted together. The type of connector, threaded, welded, or bolted, will depend on the kind of service the system's used for. When replacing a connector, always install the same type as the original. As we discuss various fittings, we'll be looking at threaded parts, but remember they can also be flanged or welded. A common threaded connection is the union. It has female threads on both ends with a large threaded nut that pulls the two halves together. You'll see these union connections on low pressure systems. This is a common 90-degree elbow connection. These elbows come in many other angles and are used to change the direction of the pipe run. A special type of elbow is called a street L, or street elbow. One end has female threads on it, the other end is fitted with male threads. This connector is designed for use in confined areas. To separate a flow from one common pipeline, a T, Y, or cross-fitting can be used. This pipe cap is used to close off a dead-ended run of pipe. It's threaded over the end of the pipe. A pipe plug can also be used. It threads into the pipe rather than fitting over it like the cap. Still another connector is the nipple. It has male threads on both ends, which are fitted into a line of pipe to connect two female parts. Nipples, like most connectors, are available in many sizes. A coupling serves the same purpose as a nipple, except that it has female threads on both ends that will connect two male parts on a line of pipe. Now, often you will need a connector to attach different sized piping together. A bell-type reducer will do this. There are female threads on either end of this reducer. Another reducer is the bushing, with male threads on one side and female threads on the other side. A special kind of reducer or bushing is called the eccentric or offset. On the eccentric, the small outlet end is not centered as it is in other types of reducers or bushings. It looks like this. As we look at these fittings, we can see markings on them. Well, let's look at a few and talk about what they mean. On the outside of any pipe fitting, you'll find several markings. These are called service markings. They indicate the kind of service conditions the fitting can be used for. This one says 125S. And it means that the fitting can be used at 125 pounds per square inch steam service. On this fitting, there's the number 275 and the letters WOG. It may be used in water, oil, or gas systems up to 275 pounds per square inch of pressure. A steam service fitting, such as the 125S PSI we just saw, may have a higher pressure rating if something other than saturated steam is flowing through the pipe system. For this reason, always check the manufacturer's instructions before using any fitting for service that is not indicated on the markings. Now, so far, we've discussed the importance of inspecting pipe systems carefully and regularly. A dented pipe or a small leak can affect the efficiency of a system, and if not repaired quickly, can cause further damage to the pipe and prolonged repairs. We've talked about how pipe is measured and sized. Finally, we looked at some of the ways that lengths of pipe are fitted together to form a system. We'll read over your text now, and afterwards we'll talk about how piping is laid out, measured to fit into a system, and cut. We're going to talk about the three main steps taken when installing a new piece of pipe in a plant system. And we'll start with the procedure for laying out and measuring a new piece of pipe. If the pipe you're replacing is still attached to the line, you can use it as a pattern for laying out and measuring the new piece. But suppose it has already been removed. Well, let's look at how you would decide the path the new pipe will follow. A precise measurement of your layout is very difficult to make unless you can figure exactly where you'll be putting the joints. But there are some things you can do to get a good fit for the new pipe. First, consider the length of pipe you'll be using, such as 8, 10, or 20-foot lengths. When you know that, you can better judge where the connecting joints will go. It's helpful to make a rough sketch of the layouts. This will help you to figure the allowances needed for making connecting joints or elbow joints. Now remember, some of the joints overlap, like on a coupling. So be sure you total up your parts' lengths correctly. For example, there must be enough space between lengths of pipe to install a joint. If you have a 20-foot space, two 10-foot lengths of pipe will not fit. One will have to be shortened. Remember, too, that threads should be engaged without pulling on the components. This would put excess stress on components or other connectors. Once you know what length pipe you need, where the joints will be, and how it will be laid out to fit, you're ready to cut it. The pipe is placed in a vise to hold it steady during the cutting process, and it's marked where the cut will be made. We'll use a 4-wheel roller cutting tool. It works well on fairly lightweight pipe that has a small diameter. After the cutter is attached to the pipe at the cut mark, it is rotated back and forth. And notice that the handle is tightened periodically as the cut is being made. Pipe can be cut in other ways, using other types of tools. A single wheel cutter, which we'll demonstrate later to cut a piece of tubing, requires a full circle rotation as the cut is made, rather than the back and forth motion that the 4-wheel cutter allows. When cutting very heavy pipe, a hacksaw or a power cutting tool should be used. Be sure to catch the cut part of the pipe to keep it from being damaged. An external shoulder is usually formed when a pipe is cut with a wheel and roller. This is removed with a file or grinder. Now, it's important that the shoulder be smoothed out completely. If it's not, the threading die won't seat properly on the end of the pipe, and you'll have difficulty starting the cutting die. Make sure that the rim of the cut pipe is also smoothed out with a file. Burrs that form on the inside of the pipe must be removed as well. A file or reamer will do the job. These pipe burrs must be removed completely, or they may collect foreign material and cause a buildup that could eventually obstruct flow through the pipe. Now, we're ready to thread the pipe. You'll have to select the proper size pipe die and make sure that the die thread is clean and undamaged before you begin. The starter end of the die has large, shallow lead threads. Now, the lead thread will take a small cut, and each successive thread will take a deeper cut until the proper depth is reached. Be sure to apply cutting oil whenever cutting threads. This reduces friction that can cause galling of the pipe and die threads. Cutting oil is needed also when using a power threader to lubricate the die and pipe threads. Notice how hot the pipe has become. We'll continue to apply cutting oil as necessary. You'll probably need to do this several times as you thread the die on the pipe. When the proper depth is reached, usually one thread through the die, reverse the ratchet. This will reverse your motion so that the die is threaded off of the pipe. Wipe the oil off of the new threads and check them. They should be smooth and cleanly cut. Now, we'll see how a pipe is cut and threaded in a power cutting device. The cut mark is made, and the pipe is slid through the motor and cutter. Then, the chuck is tightened to hold and center the pipe in place. Always wear goggles when cutting a pipe in this manner. Turn on the machine and tighten the handle until the cutter comes in contact with the pipe. As the pipe rotates, the cutting wheel will cut the pipe. Keep turning the cutting wheel handle as the pipe is cut. Be sure to catch the part of the pipe that is cut off. Now, loosen the cutting wheel handle. Turn off the motor and loosen the chuck. The pipe is now put into position for threading. Tighten the chuck again to secure the pipe. First, lower the reamer. As it penetrates the pipe, it removes the burrs that were formed as the pipe was cut. Turn off the motor and lift up the reamer. Put the cutting die in place and turn the motor on again. Bring the die in contact with the end of the pipe so that the threads can be made. The pipe is fed through the die as cutting oil is automatically applied. Allow the cutter to continue until one thread is through the die. Then reverse the action and the die will be unthreaded from the pipe. When it is free of the pipe, turn off the motor loosen the chuck and remove the pipe. Now, inspect the threads. When the threads are completed, the pipe segments can be connected. Another way of making connections between stationary plant components is with tubing. It is used in the same way as pipe, but there are differences that you'll need to know about. We'll talk more about tubing after you've read over your text and cleared up any points that you're not sure about. This is tubing. You can tell at a glance that it is smaller in width than most piping we've been looking at, and it appears to be more flexible because of all of the curves and bends. But what are the other differences between tubing and pipes? Well, there actually is no clear definition of tubing or pipe that readily distinguishes one from the other. They are defined or labeled as such by their manufacturer. If the manufacturer calls the product tubing, then we call it tubing. If it's labeled pipe, then we call it pipe. The only distinction made by most manufacturers is this. Pipe that measures up to 12 inches in diameter is labeled by its nominal size. Now, the nominal size is always smaller than the actual size of the pipe. Tubing, however, is normally labeled by the actual dimension of its outside diameter. In industrial plants, system specifications will indicate whether to use pipe or tubing to connect operational components. The specifications will also give the size, so many inches or feet, specifying if it is nominal size and the schedule of the material required. The system specifications are the requirements that were set up when the system was designed, and they'll include any modifications that have been made to the system. If you're ever in doubt about what to use, ask your supervisor. The flexibility of tubing is a definite advantage. Many of the fittings required on a pipe system to make it bend or turn a corner are not needed on tubing. Tubing is supplied in many forms, long lengths similar to pipe, in rolls, or in coils like those used for instrument connections. Fittings used with tubing are similar to those that connect pieces of pipe. The manner in which they are connected to the pipe may be different, but their shape is basically the same. The T-fitting, for example, is used on both pipe and tubing, as well as the union and the elbow. These types of fittings are the common ones that you'll find as connections for tubing. However, there's a wide variety of T's, elbows, and unions used on tubing. Most are much smaller than the fittings used on pipe. This is an elbow fitting. Although tubing can be bent, this elbow is used to make a sharp turn where space is limited. As the name implies, the union fitting connects two pieces of tubing together. If three pieces of tubing are joined, a T-fitting is used. And if multiple connections from the same supply line of tubing are required, a special manifold like this can be used. There are three ways that these fittings are connected to tubing: by threading, flaring, or compressing. The threaded fittings on tubing are similar to pipe fittings. On the flare method, the fitting is placed on the tube, and then the tube is flared. The flare keeps the fitting from coming off and also provides a seal against leakage. The third method of attaching a fitting to tubing is with a compression fitting. Now, compression fittings are manufactured in several styles. However, all styles are placed on the tube after the fitting nut has been attached. As the fitting is tightened, the ferrule is compressed on the tubing to prevent the fitting from coming off, and it helps to form the seal. There are a few things you should remember about using the flare method of connecting tubes. Both ends of the tubing must use a flared fitting because it won't match with a non-flared fitting. The burrs on the end of the tube must be removed with a reamer. Then the tube end is filed to a smooth finish. The tube is flared by using a split die block. The die block has various sized holes that fit different sizes of tubing. The tubing is fit into the die block, and the die block is clamped shut. Now, the amount of tubing that protrudes above the die block face determines the diameter of the flare. The flaring tool yoke with the flare cone is slid over the die block, aligning the point of the cone with the center of the tubing. The T-handle of the flaring tool is rotated, driving the cone into the tube. As the cone is rotated by the T-handle, the tubing is forced out to form the flare. The flare must be wide enough to seat properly, but small enough so that it will not interfere with the threads of the flare nut. If not enough tubing is left above the die block, the flare will be too thin, and a flare that's too thin is weak and may split. In addition to this flaring tool method, there are also power flaring tools which work in essentially the same way as the manual method of tube flaring. Well, that's basically how tubing is flared. There are some problems, however, when the tubing is seamed. Seam tubing is difficult to flare. It's quite likely to split at the seam. For this reason, the compression fitting works much better with seamed tubing. Let's see how this fitting is applied to some seamed tubing. Before the fittings can be installed, the seam tube should be cut to the proper length. Measuring for the length needed is done in the same way it's done for pipe and for seamless tubing. If it's replacement tubing, the old tube can be used as a pattern. Now, when the proper length is figured, the tube is cut with a wheel and roller tube cutter, which is easy to use and gives a smooth cut. A hacksaw will work, but may give a rougher cut than the roller tube cutter. When the tube is large, a power tool may be needed to cut it. As with pipe, once the tube is cut, burrs and the shoulder are removed, and the tube is reamed. Now we are ready to install the compression fitting on this piece of seam tubing. The ferrule nut is put on the tube. Then the ferrule, or compression piece, is placed on the tube. The two ends are threaded together, and as they're tightened, the ferrule is compressed against the tube to provide the seal. Be careful not to over-tighten the fitting. This will strip or break the thread crowns, which will prevent them from holding together. Bending may seem like a simple task, but it can be tricky. If it's bent the wrong way, you may end up with a crimp in the tube. When that happens, the tube is ruined because a crimp will prevent proper flow through the tube. To do the job correctly, a bender is used. For a lightweight tube, such as a piece of copper tube, a spring bender can be used. Hand benders are made differently to fit specific sizes of tubing. Here's one that will bend this heavier piece of tube. Again, put the tube into the bender, moving the slide handle so the tube fits securely. Then bend it on the mandrel until the desired angle is made. A long-handled bender is usually used for heavy tubing, and for large tubing, a hydraulic bender may be needed. But even with a bender, a piece of tube can be improperly bent. The tube and bender must be aligned correctly, and the tube must be held securely in the bender as the bend is made. Now, this is a good bend. Let's look at a few bends that are not right and talk about some of the reasons why the bends did not turn out to be correct. Notice that on the good bend there are no wrinkles, no kinks or flat areas. But on this tube, there are wrinkles here along the inside of the bend. Now, this is usually caused by bending thin-walled tubing without adequate support of the mandrel. A kinked bend also can be caused by inadequate support of the mandrel. Flattening at the bend is caused when the tubing is not securely held in the bender, causing the tube to slip as the bend is made. Tubes must be firmly clamped in the bender to prevent them from slipping as the bend is made. Practice is the best way to learn how to use a bender properly, and it's best to practice with different sized benders and with different weights of tubing. So once the proper bends are made, the tubing can be installed and the new hookups made. At this time, the system should be flushed and a careful check made for leaks in the new line of tubing. Any adjustments that are needed should be made before the system is put back into service. Well, let's watch now as the mechanic measures, bends, and installs a replacement line of tubing in this system. First, he puts the fitting that will attach the tube to the system in place so that he can get a precise measurement. With a ruler, he measures the distance to where the bend will be made, and then the distance to where the next bend will be made. The fitting is removed, but it will be slipped back onto the tube to make further measurements as the tube is attached to the system. Now, the mechanic will make the same measurement on the tube. And then he will mark the measurement on the tube. Once the mark is made, the tube is placed in the bender. While checking the angle on the mandrel, the mechanic will bend the tube in the right angle that is required to make the turn. Then he will mark the distance to where the second bend is to be made, and again will mark it on the tube, drawing his line all the way around the tube. The tube is put into the bender once more and tightly secured so it won't slip during bending. Then the second bend is made just as the first one was done. Now he will connect the tube to the system so he can check his work. The tube is connected and the fitting is tightened. The first two bends are fine. Now this time he is able to use a piece of the old tube in figuring the course of the replacement. The old tube will serve as his guide as he prepares to make the final bends in the new line of tube. Again, the mechanic carefully takes his measurement, making sure that his angle will be correct. Then he removes the old and the new tube and marks the new piece at the pre-measured point, going all the way around the tube. Now, he can attach the bender to the tube, as he has done before, and make the bend. Then he is ready to measure for cutting. The tube is again fit into place. Now he can mark the cutting place for the tube. And to make the cut, the tube is detached. The cut is made with a cutting tool attached at the pre-marked place on the tube. The cutter is rotated around the tube until the cut is made. As before, burrs are removed with a reamer, and the end of the tube is filed to smooth it out. The reamer is used again in case any more burrs were formed as the mechanic was filing the end of the tube. He'll file it once more to ensure a good, clean end. Then, before he flares the cut end of the tube, he will put both of the fittings onto the tube. The die is attached to make the flare and tightened. The flare is made as before with the flaring tool yoke turning the T handle in a clockwise direction. The fitting is then rolled up to the newly flared end of the tube. Now, when each of the fittings is attached to the system, the mechanic tightens them with his wrench, and his job is done. Well, that wraps up our discussion on tubing installation. We've seen that tubing is much more flexible than pipe and can be installed with fewer fittings than pipe. We've talked about various types of elbow and union fittings, and we've looked at how a piece of tube is flared, threaded, or compressed to connect with more tubing or to a component. Finally, we've seen how tubing is properly bent and installed. You'll find that there are many variations on these basic ways to install tubing, so always check the manufacturer's instructions and your plant specifications before you begin your work. Next, we'll take a look at flexible hoses. But first, take time to review your text and check any problems you may have with your instructor. We've seen how pipe and tubing systems are fitted and lined up to form connections between components. Tubing is generally more flexible than pipe, but it is still rigid. Tubes must be properly bent to turn corners or curve into small areas, and of course, pipe must be equipped with elbows and other fittings to turn it all. Well, there's one type of connector that is very flexible: hose. Although not as common around most plants as pipes and tubing, flexible hoses are used to carry liquids and gases from one point to another in the same manner. The materials used to make hoses, as well as pipes and tubing, are chosen with particular conditions in mind, such as temperature, pressure, and type fluid to be carried. The difference is that materials used for hosing are always flexible. Now, the flexible hose has several advantages over rigid pipe and tubing. One of the most important advantages is that it allows for movement, large amounts of movement. Imagine firemen trying to fight a fire with a line of pipe or tubing instead of a hose. It would be difficult, even impossible, in most instances. Hoses also are used effectively in hydraulic systems, which by their nature create movement or shock along the lines of their connectors. Hoses can absorb this shock and move freely, while rigid pipe or tubing can only transmit them, which eventually weakens the material strength of the pipe or tube. In addition to their flexibility, hoses are vibration dampeners. Many components vibrate when they're in operation, and the vibrations are carried along the connecting lines. When rigid pipe or tubing are continuously flexed by vibrations, they'll eventually break. A hose will give with the vibrations, which dampens the impact. Finally, flexible hoses tend to deteriorate gradually, while pipe or tubing often will burst suddenly. Signs of deterioration in flexible hosing are cracks or splits or bulges. These signs usually can be detected before a break occurs through careful, routine inspection. Now let's take a look at how hoses are measured and sized. We know that pipe is listed by a nominal size that is always smaller than the actual size of the pipe, and that tubing is listed by the size that is of its outside diameter. Well, flexible hose is listed differently than either pipe or tubing. It is sized by the measurement of the inside diameter. A method called the dash system is used to identify hose sizes. This system works by converting the inside diameter to 1/16 of an inch. So, a 1/4 inch inside diameter would convert to 4/16. The numerator, or the top number of the fraction, is the dash size. This means that a hose with a 1/4 inside diameter has a dash size of 4. It is written with the dash and then the 4. By using the dash system, you can match and connect a hose with a pipe or tube and be assured that the inside diameter of each will be the same, thus ensuring an even flow through the two lines when they're fitted together. Flexible hosing comes in a variety of sizes up to about 24 inches. Now, once the hose is built, pressure and vacuum ratings are determined. Vacuum ratings determine the amount of suction or vacuum the hose can withstand before it will collapse. Pressure ratings are made on the basis of two considerations. The first is burst pressure, or the amount of pressure a hose can withstand before it'll burst. The second is working pressure, or the normal system operating pressure. For most hoses, the normal system pressure may be decreased during operation, but it cannot be increased. Normal operating pressure is usually rated at 1/4 of the estimated pressure that would be required to burst the hose. Thus, the safety factor for hoses rated in this way is quite high. Flexible hoses are available in 3 general pressure ranges: low, medium, and high. When hosing is selected for a particular location in a plant system, pressure and vacuum ratings must be considered. In addition, environmental conditions, especially temperature levels inside and outside of the hose, will also help to determine the type of hose that is best suited for the job. The next step after selecting the appropriate hosing is, of course, installing it for operation. There are some simple but important rules to follow to ensure proper installation and an extended life for the hose. For instance, hosing should never be twisted as it is installed. Twisting can cause hose fittings to loosen, which could cause leakage when the system is in operation. Hoses should never be stretched when installed. A good rule of thumb is to allow an extra 5 to 10% of the total hose length for slack. This also provides for freedom of movement when system pressure is exerted on the hose. When bending hoses, be sure to follow the manufacturer's recommendations for minimum bend radius. The minimum bend radius is usually based on size, reinforcement thickness, and pressure ratings of the hose. Kinking and damaging stress can result when a hose is bent too sharply. In addition, the bursting pressure of the hose is likely to be reduced below its rated pressure. Finally, hoses should be protected from rubbing against other plant equipment. This can cause undue wear to the outer layers of the hose, as well as possible damage to the other plant equipment. Protective shields or supports may be necessary to keep the hose out of contact with other plant components. When installing flexible hoses, connectors will be needed just as they are with pipe and tubing. The type of connector used with hoses usually depends on the pressure service of the system. For low pressure systems, a simple push-in connector can be used. As pressure ratings increase, the connectors must be made more firmly attached. Clamps or crimping are common ways of attaching fittings on medium pressure hoses. For high pressure system hoses, the connectors may have a special surface that'll grip the woven cloth or metal mesh covering of the hose. Some hoses are stripped to the metal mesh reinforcement layer to install a fitting. This stripping or peeling back of the outer layer of the hose is called skiving. The connector that is placed on the hose in this process is called a skived fitting. Well, let's watch now as the mechanic installs reusable fittings, first on a threaded hose and then afterwards on a hose with a skived end. First, the socket is separated from the nipple of the fitting. Then the socket is put into the vise to hold it securely as the end of the hose is threaded into it. Always start carefully to ensure that the hose is not damaged as it is threaded into the socket. When the hose is completely into the socket, release the vise and check to see that the hose is properly installed and bottomed in the socket. Now the hose is turned around and placed into the vise again. Make sure that the socket is held in place so the nipple and mandrel can be tightly attached. Thread the mandrel through the nipple and using a double wrench, tighten the nipple and mandrel together. Then lubricate the nipple and the socket threads. Now, thread this assembly into the socket of the hose in a clockwise motion. The mandrel forces the hose apart and allows the nipple to slide into the hose without damaging it. Thread the nipple-mandrel combination into the socket. However, be sure to leave about a 1/16 of an inch gap between the nipple and the socket. The nipple nut must be able to swivel freely. In this way, another fitting can be threaded to the nut of the nipple. When the connection is complete, hold the nipple bolt securely with a wrench as the mandrel is removed. Then release the vise, take out the hose, and check the fitting. Now we'll see how a hose with a skived end is attached to a fitting. On this fitting, a mandrel is not used. The marks on the socket indicate how much hose is to be skived. As before, the fitting is unscrewed. This is the skived end of the hose. The outside rubber coating has been removed to allow the hose to fit into the socket. Now, put the socket into the vise so it will be held securely as the skived end of the hose is threaded into it. The skiving acts as a guide to indicate when the hose has been threaded completely into the socket. Release the vise, turn the hose around, and place it back into the vise, making sure that the socket is held securely by the vise. Lubricate the nipple and socket. Then thread the nipple into the socket with a wrench using a clockwise motion. Notice that this is a double nut nipple and that the mechanic tightens only the forward nut. The outer nut is allowed to swivel freely so that another fitting may be attached to it if more hosing is needed on this line. The nut on the non-mandrel fitting causes this type fitting to be thicker with a smaller inside diameter than the fitting that requires the mandrel. This may cause some flow restrictions and must be considered when selecting a fitting. Then release the vise and check the fitting. As with pipe and tubing, newly installed hoses are checked for leakage around the fittings when the system begins operation, and any needed adjustments are made. Well, in our discussion of flexible hoses, we've talked about how they compare with pipe and tubing as a form of connection between plant components. We've seen how the flexibility of hoses gives them many advantages over pipe and tubing. We've talked about how hoses are sized, constructed into reinforcement layers, and how they're installed. Finally, we saw the types of fittings that are used for different pressure requirements. Well, that ends our unit on pipes and pipe fittings. Be sure to go over the information in your text and settle any questions you might have with your instructor. And be sure, too, that you always consult the manufacturer's instructions and your own plant manual when working on any pipe, tubing, or hose system. It'll help to ensure a job well done.